In the middle of the 20th century, in the 50s, there was an important movement in the statistical field that started questioning the foundations of the field. In particular, what is the meaning of probability, and are we doing the best that we could do with data if we use the classical methods? So a new movement that's called the Neo-Bayes Laplace Revolution came out, and there are some very big names associated with it. James and Stein were econometricians in the west coast of the United States, Professor Lindley from University College in London, Professor George Box at the University of Wisconsin-Madison, and Professor Zellner also at the University of Wisconsin-Madison. But Zellner then was offered a job by the University of Chicago Business Schools. A professor in business school in the US made a lot more money than professor of statistics. So Zellner moved to Chicago, and he was a celebrated Bayesian statistician. So this is a photo of Bayes. His paper was published in 1763. It was a statement of conditional probability. This is a photo of Pierre-Simon de Laplace. He was a French nobleman that he liked to do applied mathematics. So he used statistical method for astronomy, for biology, but he was actually using Bayesian methods, but he called it inverse probability. And actually, Laplace had the right view, in the sense, this, if you translate into English, is memory on the probability of causes as measured by the events. And that's exactly what we want to do in science. We observe things, and then we try to think about what causes the observations. Whereas classical statistics is the opposite. You postulate something that you call a model, that you think is a causal representation, and then you see with what probabilities you observe the effects. Okay, so it's exactly the opposite, but this is really what the mind wants you to do, is to measure your uncertainty about the causes once you learn the effects. The basic idea in Bayesian inference is that to construct a distribution that represents your uncertainty before you observe data. Then you observe data and represent the contribution of the data in this red curve that's called the likelihood function. And the Bayesian analysis produces a final distribution that is called the posterior distribution that is typically in between the prior and the likelihood. If the data is not very informative, then the posterior is close to the prior. If the data is very powerful, like experiments of very large scale and very good resolution, then the posterior is very close to the likelihood. So I will pass this, but it is important to note, but because the priors are subjective most of the times, then it is important to measure the extent of Bayesian learning, or said, in other words, what is the influence of the prior on the posterior? Because if the prior is very influential, I could change the prior and get a different answer, and I could find the prior that gives me the answer I want to find, which of course is not very scientific. Okay, I have been told many times, I don't know if this is fair or not, of being responsible for introducing Bayesian methods in animal breeding. And the story of this is that in 1982, I went to France for a sabbatical, and I started collaborating with a French animal geneticist called Jean-Louis Foulet, and we were interested in analysis of categorical data, like being alive or being dead, or different grades of a disease. And we tried to do the same thing that was what Blapp was doing, but with categorical data. So we found that the Bayesian way was one way of doing it. And then I started thinking how this could be adapted to many different problems. And I discussed this with Rohan Fernando, who was my student and colleague at the University of Illinois, and we wrote this paper, which in some respect is the introduction of Bayesian methods to animal breeding in a formal manner. And then another student of mine, Kunshan Wang, originally from China, from Nanjing, but now he's working with this pharmaceutical company in the US Pfizer. We were the first one in the world, I think, that introduced a class of methods called Markov chain Monte Carlo, specifically Gibbs sampling. This paper was published in 1993, but it took about a couple of years to get a review and to get it published. But the first time that we presented Gibbs sampling was in 1991 in a small abstract. Okay. This methodology, Markov chain Monte Carlo, is one that allows you to do almost anything you want. So you can come up with very strange and extravagant prior distributions. This is dangerous because extravagant prior is like drinking too much before you drive or drinking too much before you do anything. Then you combine with the data, and if your prior is very extravagant, the posterior will typically be very colorful. So you can actually fit any model, but sometimes you can get results that are, instead of reflecting the information content of the data, will reflect whatever the prior is telling you. So that's why I'm saying that it's important to measure the extent of Bayesian learning. And it was not until we started, perhaps single-handedly, to try to convince colleagues that Bayesian methods were very useful and very powerful. Then there was an explosion in genetics as soon as the Markov chain Monte Carlo methods began. So today, Bayesian methods are used for everything. And in agriculture, the epitome is what we call genomic selection, which we will talk a little bit more.